In this video, we're going to be looking at um, the proportionality of Coulomb's law. And so what that means is that we'll be investigating situations with no numbers, at least in terms of values for Q1 and Q2. But instead, we'll be looking at how proportional changes in those values change the force, or how, if force remains constant, proportional changes in those values change other values in the problem. So what we're going to start with, if we recall, is the equation. And so the equation that we had before say it with me, is that the force is equal to K Q1 Q2 over R squared, the distance between the two objects squared. Let's clean that up a little. And as you can imagine, this looks formidable, but is not as bad as it could be. In fact, we'll know all of these but one thing. Now, recall that K is always going to be 9 billion. And the unit for that is, again, Newton meters squared over coulombs squared, where Coulomb is the unit of charge. And you'll have seen that in another video. And so what we're going to look at now is some proportionality questions. The first question is, let's say I have two particles a certain distance apart. Distance r apart. So I have this, and maybe they're both, let's say they're both negative for now. They're a distance r apart. Now the question is, if I double the distance between them, how does the force change? And we know that the force changes via this equation. So let's talk about a strategy here. So there are a couple ways to approach this. The first way is to consider what happens when, when everything else remains the same. So I don't need to consider the other things. All I need to consider is the effect on r squared, the r squared in the denominator, because the distance is r here. And so what I can look at is I can effectively reduce this to an equation that looks like this. Because in this case, I know that K doesn't change. So that can't affect anything. So K doesn't change, Q1 doesn't change, and Q2 doesn't change. So those are all inconsequential to the force. The only thing that matters is this r squared in the bottom. And so if the only thing that's changing is the distance, then I can look at how the distance changes. So I compare that to the force equaling 1 over 2r squared. I doubled the distance, I made it twice as big, so I have to do 2r squared. But if I expand that out, that's equal to 1 over 4r squared, which is equal to 1/4 of 1 over r squared. But 1 over r squared is our original force, so we have 1/4 of the original force. This number effectively, and the coefficient that we get out of all of these, this number tells me how the force changes. So this tells me that the new force is 1/4 of the old force. So 1/4 as big. The force is 1/4 as big. Okay, let's do some erasing here. Let's try another problem and let's look at a slightly different approach. Okay. So instead of two particles, we'll have two particles r apart still. Let's go for here. And it's still the minus. And they have charges Q1 and Q2. And I want to know what will happen if A, Q1 is doubled, B, Q1 is doubled, and R is cut in half, meaning I'm twice as close. This R is half as big now. They're closer. And then C, all values, meaning Q1, Q2, and R are doubled. And I want to know, and the question is always, what happens to the force? Not talking Star Wars here, we're talking about the more mundane physical forces of the world. Well, it's only mundane if you don't think about it too closely. I mean, these things aren't connected by anything and yet can pull things toward them. So in some sense, it's better because it's real. Okay, so we're going to get back to this question of what happens if the charge is doubled, what happens if the charge is doubled and R is cut in half, and what happens if all the values are doubled. So let's start out by looking at A. So we'll look at A over here. And the question is, okay, so I have the force, and we know it's equal to KQ1, Q2 over R squared. But effectively, some of these things don't matter. The K, the Q2, and the R squared don't do anything for us, so we can sort of ignore them. We can set them to 1. They have changed by a factor of 1. So really, on the right side, I write down, I replace each variable by the amount of change, by the factor of change. And so that turns into F is equal to the new value. So when we do this, we're looking at the new value. The new F is equal to 1 for K times 2 for the Q1 times 1 for the Q2 over 1 for the R squared, 1 squared. And so that's just equal to 1 times 2 times 1 is 2 on top over 1 on the bottom, which is 2. And as I mentioned before, this is the proportionality, or this is the value that we scale by. This is, so we doubled the force. If we double the charge, we double the force. And that makes sense. We multiply one of these elements by 2, well then we have to do the same on the other side to make it match. The force gets doubled. You can think of it algebraically by saying if I change one of these things, I have to do the same operation on the other side. So if I multiply this by 2, I have to do a times 2 multiplication on that side. And that's the only thing that changes. Likewise, if in our previous example, if I multiply the R by 2, well, remember that goes inside these parentheses here. So I multiply the R by 2, so that gets squared, and that's in the denominator, so it's the same as multiplying this by 1/4, and then the equations balance out. That value will cancel, and we'll have the same relationship. And so that is another way of thinking about this. Okay, now let's move on to part B. For part B, we have Q1 doubled, and so F equals K Q1 Q2 over R squared. And again, I'm going to do this way here with replacing the variables with the amount they change by. K is never going to change, so we can basically ignore that. Now I'm going to use a sort of darker green. And so what I get is that the new F is equal to 1. The K didn't change, so it's just multiplied by 1, times Q1 is doubled, so times 2 on the top. Q2 doesn't change, so it stays at 1. We multiply it by 1 because it doesn't change. Then we divide by R cut in half. So that means that we have something squared, and R is cut in half. Okay, and so when we solve all of this, we should be able to figure out the actual amount that we change by. And so we get that F is equal to 1 times 2 times 1, which is 2 on top. And the R we can consider to be a 1. So really we have 1/2 in the bottom there. I'll change that here. And so over 1/2, because we're getting rid of all the variables, right? So we cut it in half, so we replace it with the 1/2. So 1/2 squared. But this is equal to 2 over 1/4, which is equal to 8. I'm dividing by a fraction, so I multiply it by the reciprocal, and I get a force that is 8 times as big. When I double Q1 and I cut R in half, well, first I'm doubling the force, and then cutting R in half makes it 4 times bigger. I'm closer, so it's stronger. And so that is for part B. Okay. Now let's erase some of these and go to part C. Okay. Maybe if I select these and then I can erase, let's delete. Oh, great, that works. Learning new things every day. It's one of the pleasures of living. Okay. So now finally, let's get to part C. And part C is the big one. All of them are doubled. And so we're going to use, I don't know, let's use a blue. Okay. And so, oh, that's not working very well for me. Oh, because I'm not drawing. There we go. Okay, so now let's go to C. And C says, again, we're going to start with our basic formula, just as a reminder. And when you're solving for this, all you do is plug values in. So I'll give an example of that later in another video, but it's not a particularly thought-intensive process. So I'm not going to spend a huge amount of time on that. Okay. So the new force is going to be, well, what are we changing? Well, K stays the same. And then Q1 is doubled. So we multiply by 2. Q2 is doubled, so we'll replace that with a 2. And then R is doubled, so we'll divide by 2, because we're replacing R with twice as much, squared. And so what we get on top is we get 4. 1 times 2 times 2 is 4. And then we're dividing by, what's 2 squared? Well, 2 squared is 4. Let's remember our numbers here. Very important thing, going back to kindergarten. And 4 over 4 is just 1. And so the force is the same as it was before. If we double everything, well, the radius squared takes care of the doubling of the charges. So we move farther away, so it gets weaker, but we increase the size of our charges. They're charged up. And so they make it stronger again. And the way those things balance out in this equation is that the force actually won't change if everything is doubled. So that's a view of messing around with proportionality. Hopefully you picked up a trick or two, or maybe you have a comment about how terrible I am at this. But either way, hope it was helpful or entertaining at least. And we'll see you next time.